Hi everybody, this is Cal with sections 13.3 and 13.4. Section 13.3 is called Arc Length and Curvature. Section starts with a discussion of what is arc length and some formulas for arc length, which we can see at the bottom of 877, top of 878. For those who remember your Calc 2 or have done the pre-homework for this course, these formulas should be relatively familiar, make a certain amount of sense from what you've known before. I would say that just if you're going to memorize something, memorizing box 3 should make a lot of sense. And hopefully that should make sense geometrically as well. The arc length is the integral of the speed of the curve. I mean, length is integral of the speed, because integral of the speed is distance traveled. So hopefully that should make a certain amount of sense. Example 1 is a really great fundamental example. Make sure that you follow through it and understand what's going on, because it's going to be used in future examples in this section. Now, right below example 1, starting in the middle of the page, there's a really good discussion about how more than one vector function can represent the same curve in space, and these are called different parameterizations of the same curve. Now, it tells you that to tell you another story and doesn't really necessarily make that clear. The idea here is that arc length doesn't depend on which parameterization you've chosen. And so it makes sense to define what's called the arc length function. You should make sure you understand what that is and how it's found. And furthermore, that you can use that arc length function to parameterize your curve. I recommend that you read through this note at the top of 879 and example 2 that shows the process in action to show how to reparameterize a curve with respect to arc length. This makes it so that the speed that you move along the curve is 1 all the time. If you literally take r prime of t and take its norm, take its length, you'll get a 1 the entire time. That means you're traveling along the curve at a constant speed of 1. That's the value of reparameterizing with respect to arc length, and it can be a really nice thing to do. After that, we get into a discussion of curvature. For now, you can sort of take curvature as a whole bunch of formulas that are a little bit hard to memorize. You would almost never use this definition to actually calculate curvature, but it does give you a good idea of what curvature is. It's the derivative of the unit tangent vector in terms of speed, where speed is s. Why is that interesting? Well, the unit tangent vector, it's the direction of the curve where we've divided by the length. We don't care how fast the curve is moving when we're talking about a unit tangent. We care what direction it's going. And so if I take the derivative of the direction the curve is going with respect to the speed we're moving along that curve, what the curvature really is how fast is the direction of the curve changing. So a large curvature means that we're changing direction very quickly, and a small curvature means that we're changing direction very slowly. A curvature of 0 should mean that we're going in a straight line at that point. Note, by the way, that curvature is definitely a function of time, which maybe is not clear from this definition. Going on to the next page, we have a couple more formulas on this page that we could actually use to compute curvature. I really like Theorem 10 as my go-to of how to compute curvature, although box 9 can be useful too. You don't have to worry about the proof of Theorem 10. You might want to look at example 3 where they compute the curvature for this circle. On page 881, they have an example of finding the curvature of another curve, which is nice. And Theorem 11, or box 11 rather, is another formula for curvature, which is really specific to a certain, for the case where you have a plane curve with equation y equals f of x, where this is parameterized in terms of x equals x, y equals f of x. And this can be useful for some cases. Do read the discussion and understand the formula. Example 5 shows it in action, which is nice. Going into 882, we have a discussion of the normal and binormal vectors, and this stuff is pretty cool. The unit normal vector, it's like the unit tangent vector. The unit tangent vector points in the direction the curve is going. The unit normal vector points in the direction that the curve is curving. It's the derivative of the unit tangent over its length, so it's literally the direction that the unit tangent is curving towards, if that made any sense. Once you have the unit normal and the unit tangent, you've got two vectors, and if you want to round out 3 space and have 3 vectors to describe 3 space, you can get a third one called the binormal by crossing the first 2, taking the unit tangent across the unit normal. This gives you, the book doesn't say it here, but this gives you what's called the floating frame along your curve. And it gives you, well, for those who've had linear algebra, a basis for 3 space at every point along your curve. That's culture, that's not really important. Example 6 shows computation of the unit normal and binormal for the same circular helix that you've been using for the entire section. At the top of 883 is a really cool bit of discussion, talking about a little bit of geometry behind space curves. It gives you the normal plane, which is everything orthogonal to the tangent vector, and it's the plane determined by the normal and binormal vectors. It also talks about the osculating plane. This is the plane that is comprised of the tangent and normal vectors. It's sort of the plane, call it tangent to the curve at that point. It's the plane that includes the direction the curve is going in and the direction that the curve is curving towards at that point. The cool thing about the oscillating plane, if you draw a circle in it that fits the curve, called the osculating circle, then the curvature of your plane is 1 over the radius of that circle, which gives you a nice geometrical, intuitive definition of curvature. You don't really have to pay a heck of a lot of attention to examples 7 and 8. I would consider page 883 to be mostly culture for our purposes. But at the bottom of the page, there's a really nice summation of a lot of the formulas that you need from this section. Skipping through the exercises, we're going to move to section 13.4, which is motion in space, velocity and acceleration. Now, most of this section should be really familiar from things that you've done in Calc 1. I'm going to skip right over the first page here, except for the basic definitions. The velocity vector is the, if r of t gives you the position vector of a particle, then its first derivative is certainly your velocity vector. The length of your velocity vector is the speed. And on the top of the next page, the acceleration is the second derivative of your position vector. And again, this should all be really familiar from Calc 1. Example 1 is a good example of finding velocity, speed, and acceleration given position, as is example 2. And example 3 is a really good example of going the other way, and I suggest that you pay special attention to example 3. Note the role of constant vectors in integration. That's pretty important. Let's see. There's a little blurb here in the middle of 888 about Newton's second law of motion. Well, that's pretty important if you're going to do any physics applications. And example 4 and 5 shows that being used in a couple of physical examples. Give them a reasonable read. And that seems to continue on to page 889. Example 6 I absolutely love. It's one of our sort of standard physics setups. Take a good look at it, make sure you understand how they're doing what they're doing. Now on page 890 we get into a discussion of tangential and normal components of acceleration. Here's the idea. At any point on our curve we've got a tangent, the unit tangent vector t, we've got the unit normal vector n, and the acceleration of your curve is always going to consist just of components along those two. You can project the acceleration vector onto the tangent and onto the normal, the same way you can project a vector onto the x, y, or z axis to get its components. And this gives you a different view of the acceleration vector. It tells you how much of your acceleration is affecting your speed, that's the part that's the tangential component, and how much of your acceleration is affecting your direction of the curve, and that's the normal component. The formulas for each are basically given in this box, and you can kind of see a discussion of usage of this stuff on the next page. Make sure you read through example 7 where they compute the tangential and normal components of acceleration. Those are useful. And we're not covering Kepler's laws of planetary motion, so you can basically skip the entire rest of the section, although it might be interesting to some of the physicists in the audience. So that covers sections 13.3 and 13.4. See you next time.